slight violations in practice. Although we have these assumptions, and like in an ideal world, of course, all of them will be satisfied, but it's very common to have at least slight violations of these. And it's also important that not all violations necessarily lead to major biases. So your result might still be very close to the true value, but it's important to understand the limitations of your model. And then for that, you really need to understand what's going behind in terms of assumptions. Let's start with linearity. So if we actually already talked about linearity, in linear regression, as the name implies, we assume linear relationships between independent variables and a dependent variable. And here you see several types of relationships. And when we fit a linear regression on all of these data, the result will always be a straight line. So it will always go through the points of our data, and then, yeah, this will be the line that minimizes the vertical distance between these data points and this line, because that represents the error, right? We saw this yesterday. So for instance, if you have the violation of this linearity, in this case, for instance, if you have a quadratic relationship and you assume linear relationship, this leads to biased estimates, meaning that you are no longer representing the relationship that you want to represent. For instance, we know that this regression line is our prediction line as well, right? So if you are, for instance, going from this this value of the independent variable to this value, as you can see in real life, the true relationship is that this needs to decrease. But with the regression line, you are actually going from here to here, meaning that the value of the dependent variable actually increases. So you make wrong conclusions related to the direction of relationship for this section, for instance, in this case. It might also be that there is indeed an increasing relationship, but this is more exponential. Or it might be that you have actually a kind of a step relationship between the two. This happens, for instance, when you have generally dummy variables. Then if you just assume that this is a linear relationship, you just fit a straight line here, but actually these sections don't have any representation of data. So overall, linearity is something you assume in the linear regression model. How do we diagnose this? How do we see that actually this assumption is satisfied or violated? Is that we can look at residual patterns, or we can have a more context-driven approach, which we will not spend a lot of time on this, but I will come to that in a minute. In the residual patterns, we always look at error term. And what is the error term when we fit the model? It turns into residuals. So the residuals, if you remember, was the predicted errors from our regression model. So in general, we look at standardized residuals, meaning that we just subtract the mean of the residuals and divide them by their standard deviation. And we also save this predicted or fitted values, meaning that we basically make a prediction for each of the data points that we have in our data. And then once we do this, you can, once you do that, if you see this kind of a non-linearity in the distribution of these points in a scatter plot of residuals versus independent variable or residuals versus fitted value, then you can see that this is not linear. So you violate the linear relationship assumption. The safe zone is that if you see a straight line around the residuals as you move along the independent variable or fitted values. And these upper graphs show the relationship between the dependent variable and the independent variable. So this is something you can already do before you fit the model. I mean, I would say this is not as common as doing it based on residuals, but before even fitting the model, you can already look at the relationship between the two and observe that this is a nonlinear relationship actually. And when you look at context-driven, there are a couple of stereotypical examples of nonlinear relationships. For instance, monetary values tend to show what's called the diminishing marginal returns. So the additional dollar you spend or additional euro you spend on top of 100 euros versus on top of 1,000 euros doesn't bring you the same utility, for instance. Okay. Or if you, basically, if you think this in terms of profits, for instance, the profit that you get, let's say you earned 2 euros from your business, the additional 1 euro would be a lot, right? But if you have already earned 1,000 euros, this additional 1 euro would not be as much as as in the case of 2 euros. So this is what's called diminishing returns. And in this case, it's very useful to, so it's a nonlinear relationship, and then using a transformation really helps. Anyways, let's move on with the how you can actually look at this linearity assumption in R. Once you have your model, so this is basically an LM object, meaning that you previously fitted the model with the LM function here and saved it in this object. You can actually plot this object. And then the first plot that comes out of this is a plot of residuals versus fitted values, which is called a residual versus fitted plot. In this plot, we want to see a linear, this red line, linear line, so that we can conclude a linear relationship, okay? As you can see here, this is nonlinear. And here it is almost linear. So I also put a note here that in practice, seeing this perfectly straight line is very much unlikely. So this this level of, let's say, linearity is acceptable. And if you actually violate this assumption, so if you conclude that your data is actually nonlinear, that like the relationship is nonlinear, then using transformations may help. So for instance, two very famous ones are log transformation and quadratic transformation. We will see these. So you can take the natural logarithm of the dependent variable, or in some cases, independent variables as well, which actually represents the nonlinear relationships. But you can still use a linear model to model the relationship. So the relationship between X and Y, so the dependent and independent variable actually is nonlinear, but the relationship between the dependence variable and the log transformed independent variable or log transformed dependent variable can be actually linear. The one in the code stands for there are 4 plots that is in that object. We will see as we move along. The first one is the fitted versus residuals plot. So there are more plots in that. So if you put 2, 3, or 4 here, you will get different kinds of plots. We will see them soon. And the quadratic means that you add a nonlinear transformation of the regressor, meaning the independence variable, to the model. So you regress y, the dependent variable, on the x and x squared. There are other kinds of transformations which we will not cover, And alternatively, you can use, for instance, a nonlinear regression. This is just for your information that it exists, but we will not go there in this course. Okay, so the second second assumption is related to normality. In a linear regression model, which we can specify like this, right? That it's a multiple linear regression. This error term actually is normally distributed with zero mean and some standard deviation, or some variance in this case. And then if we violate this normality assumption, the significance tests become unreliable. So our conclusions for significance of the estimate might be misleading. And then this means a higher chance of type 1 and type 2 error. If you remember type 1 and type 2 error, in the type 1 error, basically you actually don't have a real effect. So in this case, this man is not pregnant, but the conclusion is that your conclusion is that this person is pregnant. So this is what's also called a false positive, right? So there is no effect in reality, but you conclude that there is an effect. In the type 2 error, there is actually an effect. So in reality, this woman is pregnant, but you conclude that there is no effect, meaning that this person concludes that this woman is not pregnant. Okay, so if you violate normality, it increases both the chances of type 1 and type 2 errors. So how do we check these then? Again, this really relies on the residuals and fitted values. And you can use histograms or what's called the quantile or QQ plots. So in R, the way to get to these histograms or QQ plus is like this. So histogram of fit1. So fit1 here is your model. This is the LM object. And then you can use this dollar operator and get the residuals. So this is how you access to the residuals of a regression model. Then you can basically use a histogram to see the distribution of these residuals. And in this case, the first one, we have this beautiful normal distribution, which is also not very common to see, I would say, but this is what you want to see, okay? And then you might also see this right skewed or this concentrated around zero, but with longer tails kind of distribution. So in this case, these are non-normal, and this is the normal distribution of the residues. Or you can also use a QQ plot, and this is how you get it. So again, you use the model object, but now you use the second plot in this object. The quantile plot actually is a scatter plot of the standardized residuals and the theoretical quantiles. And these theoretical quantiles refer to the theoretical quantiles of the standard normal distribution. So what you do is actually you use the quantiles of the standard normal distribution, and then you basically look if the location of this, if the quantiles from what you see in your data fits these theoretical quantiles, meaning that if your standardized residuals are actually normally distributed. So if you see this 45-degree line, so this comes from -3, -2, etc. The same goes for here. So this is the 45-degree line. If your data points, actually, if your standardized residuals match the theoretical quantiles along this 45-degree line, then you can conclude that your residuals are distributed normally. Deviations from that, like this, so this is the 45-degree line again, and your residuals are actually showing this kind of pattern, which is then not normal, okay? So you will also play with this in the assignment, but this is important to know that like what is normal and what is not normal from QQ-plot or a histogram. So might we have actually a non-normally distributed error? It might be that actually the linearity assumption is violated. It tends to go hand in hand. Or it might be that dependent or independent variables or both are not normally distributed. Okay, all of this can actually cause errors to be non-normally distributed. And the solutions here would be, again, you can try transformations, for instance, log transformation, or in some other cases, we can actually use dummy variables if we have groups in the data. So these are just options, but these are not like transforming variables can be a go-to option, but comparing groups happens if we really have groups in our data. And when we have groups, it might be that we actually have like this kind of clusters of data points, which really violates the normality assumption. Okay, this kind of clusters. So that's why using dummies can actually, or comparing groups can actually help with the non-normality. And then other methods which we don't cover here. Assumption 3 is independence of error terms. Here, you can actually write the regression line per observation. Okay, so this I is per observation. If you ask in a survey 10,000 people, you can write the regression line for the first person, the second person, etc. But what does the error terms like the independence of error terms means that this error I, so for each individual or for each observation, this error is independent from the other. If it, like my error term is independent from the error term of another respondent. So it's, yeah, it might be a bit too vague right now, but it is generally related to if you have groups or clusters in the data. So if we come from the same neighborhood, our perceptions about certain municipal services could be very likely to be similar. So our error terms are also correlated. It might be that we have repeated measurements from the same respondent. So if you ask me something today and in 2 months, my response probably will be correlated. And then it might be related to some kind of time trend. Okay, and if you actually have dependent error terms, then you will get incorrect standard errors, confidence intervals, and p-values. So there will be a problem with the significance conclusion. And this might also, again, increase the chances of type 1 and type 2 error. The way we can diagnose this is, again, using residuals, but this time we can actually plot them through time. If we are suspecting that there might be time trends in our data. And then if you look at residuals versus time, it might be that actually there is a trend, like a positive trend. So as time goes by, your residuals, meaning that your predicted errors are actually increasing. Or it might be that it first increase, decrease, etc. So there's a pattern in your residuals versus time, for instance. In the case of independence, you should see this linear kind of distribution around time for the residuals. And this is from the residual patterns. The context-driven diagnosis, as I mentioned, that if you already have clearly defined groups or clusters in your data, or you know that you have repeated measurements in your data, you will probably violate this independence of error terms assumption. And the possible solution here is that if you have time-related issues, then you can use time series techniques. If you have cluster data, you can what's called cluster robust standard errors. You can use them to make your conclusions, but these are not covered. But know that there are solutions that exist to solve this problem. And if you look at this plot, so this up, down here, this generally is an indication of seasonality. Okay, so that's how you can also see seasonality in your data. Homoscedasticity. So this basically means that you have a homogeneous variance along your independent variables. With increasing x, your the variance of your error term stays the same. Again, if you look at this observation-based regression line, so this is individual errors, and then for each observation, the assumption is that this error term is distributed normal, zero, and sigma square. But the sigma square doesn't have an I, okay? Meaning that you actually assume the same distribution of same distribution with the same variance for all of your observations. Meaning that you actually should see, if you look at the residuals versus fitted values, for instance, you see this kind of random clouds and static. So the variance here in your lower fitted values should be similar to the variance when you have higher fitted values. If you violate this, then you might get incorrect standard errors, confidence intervals, and p-values, meaning that your conclusion related to the significance might be wrong. And then you also get, again, a higher chance of type 1 and type 2 error. Okay. Yes, so like we talk about homoscedastic, then heteroscedastic is that the variance at your lower ends might be different than the variance of residues at the higher end of the either the independent variables or the fitted values. Same goes here. The variance is in the lower values, it's quite high, and the variance actually decreases as you move along with the independent variable or the fitted values. Again, and another representation of this is also how you do the diagnostics, right? I just said you look at residuals. If there is this kind of cone-like pattern, or basically something other than this constant variance, like you can actually put two straight lines and restrict all of the residuals within that, then you always have heteroscedasticity. So here, this is how you get this diagnostic plot for homoscedasticity as the assumption. You can use the first plot, which is the residuals versus fitted plot. And if you see this even distribution around zero, so this random cloud of points, then you can say that this is homoscedastic, because as we move along with the fitted values, with increasing fitted values, we see the same variance of residues actually. There might be other situations like here, you see that everyone's residues are actually quite high, and the variance here is different than the variance in the middle. So we want random distribution, or the random cloud of points around zero. So this should be on average zero, and the variance should be similar. And here you can easily see this kind of cone-like structure. Here the variance is low, here the variance is high. So from plot one, we can make, yes, that's true. Here you can also talk about, see if this is linear or not. For instance, this one is linear, but not homoscedastic. So that's an important observation indeed. So this one is linear, but not homoscedastic. You can also use another plot to look for homoscedasticity, and that is the square root of standardized residuals versus fitted values. So this is called a scale location plot, and you get, this is in the third position of the plot that you get out of your model. This is quite similar to the previous plot, actually, but here you basically look if there is an increasing or decreasing pattern. So here it's less likely that you will see the cone shape, but you can actually rely on this this line. Basically, you again want to see this even distribution around zero along the fitted values. Still, sorry, this is not around zero, but you see a random like cloud-like distribution in this plot, basically. But then in the heteroscedastic case, there will always be a trend, like increase or decrease, or any like quadratic, etc. The meaning of tree is just this is, you can think this as a special plot function. So when you use a plot function for your linear model, so this is LM of some regression. In this model object, there are several plots saved, actually. If you, yeah, you can think it like that. And then in the third position, you will get this plot, the scale location plot. If you use 1, you will get the residuals versus fitted plot. If you use 2, then you will get a QQ plot. This is basically kind of a shortcut. So you can do all of these by hand as well. By hand meaning like you can code these and get these results. But because these are very common diagnostics that are used in regression analysis, you already have this kind of built-in options to get this diagnostic plots. So just know which one to use. Like the one is residues versus fitted. The second one is a QQ plot, and the third one is a standardized residuals. Sorry, the scale location plot. You will also see in the assignment that you can actually get 4 plots out of that. The fourth plot we never use, actually. That's related to outliers, but yeah, that's not the scope of the course. But you can basically get this 2 by 2, like 4 of the plots in one picture as well. And that's what you will see in the assignment. You will not code that yourself, but you will need to just uncomment it and see the result. Okay, if you have homoscedasticity, what you can do, like again, one option is to transform variables. The log transformation might actually help with this differences in variance. And another one is that you can use what's called a heteroscedasticity robust standard errors, which allows you to actually make right conclusions about the significance of your estimates. But this part we actually won't cover here. Yes, let's move on to the next assumption, and then I come back and show all of the plots again, okay? I'm just gonna let this stay here. The fifth assumption is related to multicollinearity. Multicollinearity means that you actually have high interrelation or high correlation between your independent variables. So this is not related to the correlation between dependent variable and independent variable, but the correlation among the independent variables. So if you, when you run a multiple linear regression, so multicollinearity can only be an issue in multiple linear regression because in the simple linear regression, you only have one independent variable. When you have a multiple linear regression, though, you can have two independent variables where their correlation is high, okay? In that case, it's very hard for model to determine how this first variable or second variable influences the dependent variable independent from the other independent variable. So let's say this variable one, variable two. You don't really know, it's very hard for the model to actually understand, identify how this variable one influences y independent from. So this is the important part, independent from the second variable. Because if you remember, we had this ceteris paribus assumption in the, or ceteris paribus condition in the multiple linear regression that the coefficient estimates were represent the change in, like, how does one unit change in a variable, an independent variable, changes the dependent variable, keeping all other independent variables constant. But in this case, if these two variables are actually moving together, if they have a high correlation, we cannot really keep one constant and change the other, right? Because these two move together. So this creates a problem in the regression models. And you can also think this as, again, like if these two variables are very similar to each other, like if they move together, like putting one over the other does not add more information, because the information of like this increase is already stored in the first variable or the second variable. If you have, if you violate no multicollinearity assumption, so if you have multicollinearity in your data between your independent variables, then you will get higher standard errors, which means that you have a higher chance of false negative conclusions. So when actually there is an effect and you conclude there is no effect. Okay, this is so not type 1 error, but type 2 error. Okay, sorry. There's also one important thing here is that in multicollinearity, we have something called perfect multicollinearity. So this is when when your variables are perfectly correlated, so 1 or -1, meaning that they actually include kind of the same information for the purpose of the model, or when one variable is a linear combination of others. So for instance, if you remember, we defined in the dummy variables in regression, we defined 3 dummies for 4 categories, or like n-1 dummy variables for n categories. That is also because if we define 4 dummies or n number of dummies, then if 3 dummies take value of 0, we represent a reference group, right? We already have that information with 3 dummies, and if we actually define the 4th dummy, then these dummies will be perfectly multicollinear. V1 and V2 are independent. Yes, I mean, yes or no. This can be that they are different concepts, but they might be still very highly correlated with each other. So this is really about the correlation, not the independence. Okay, so the diagnostic is actually related to checking correlation between explanatory variables. So you get a correlation matrix of the independent variables, and then see if there are highly correlated pairs. And when you have a correlation matrix for the purposes of the course, we will always give you a threshold of what is the high correlation or low correlation, so you will not be in between. And then if you have multicollinearity, then the solutions are, you have several solutions. The one very common one is to drop one of the variables. So let's say the 2 are very highly correlated. You drop one of them because you can actually represent this similar information with only one of the variables. And then you actually do, like, you drop the one that contributes less to the R square. So let the one that explains less of the variability in the dependent variable. So if you have, so for instance, if you have two independent variables, you drop one of them and then fit a model, you drop the other one, fit a model, and look at, for instance, the R squared. You can combine predictors, which is not very often, or you can also use factor analysis to look at uncorrelated components of these two variables, but which we will not cover it here. When is not a problem? Okay, multicollinearity is not a problem if you actually deliberately introduce it in the model. So for instance, if you add polynomials, or for instance, the quadratic term, we saw this quadratic transformation, right? Like we will add x and x square as independent variables. And of course, x and x square are perfectly correlated. I mean, almost very highly correlated, sorry, not perfectly correlated necessarily. So then adding the x square in the model will, of course, introduce multicollinearity, but this is not a problem because this is a deliberate thing. And then in forecasting, if the same kind of multicollinearity holds for the period value where you will make a forecast, then it's again not a problem. Yes, in this case, you dropped it's not the lowest R square, but it's basically which one explains more. In the example that I gave, indeed, if you just fit variable 1 regression, variable 2 regression, which one is lowest, you would want to drop that. So this is correct indeed. Okay, so the example of this is actually what we have seen yesterday. So this credit cards example from lecture 7, we had family size, then we added family income to this model, and the estimate for the family size both decreased and became insignificant. And that was actually related to a high correlation between family size and family income. So multicollinearity can cause this kind of weird conclusions. And in this case, if you notice, we make a different conclusion in terms of significance in the case where we have both family size and family income. Okay, so let's now go quickly back to the plots. So in plot 1, so here in this residual versus fitted plot, what we can look at is linearity assumption and homoscedasticity assumption. Linearity assumption is related to seeing this line, this red line, linear. Homoscedasticity is related to seeing the variance of this residuals constant. And in both of these cases, the variance is actually not constant. You see more dispersion here than here, or more dispersion here than here. The second plot is related to quantile-quantile. So this is the second plot of a regression fit. Here you have, you plot the standardized residues and the theoretical quantiles from a standard normal distribution. If these match on the 45-degree line, then you can conclude that this is your residuals are actually distributed normally. If not, so if you have this large deviations, so this kind of deviations towards the end, these are perfectly normal. Again, it's very hard to get this perfect line. But if you see this clear deviation, like this is also, even the shape is weird, from this 45-degree line, then you conclude that this is non-normal. And the third plot is another way to look at homoscedasticity again. You can both use the first plot and the third plot. In the third plot, what you want to see is a random cloud of points. And if you actually see this, you can also look at this linear line here. In the heteroscedastic case, you will always see this dispersion changing in the scale location plot and generally a trend here. Okay. So I will move on to extensions. And I want to cover standardization first, and then we can take a break. So we will now see what's called a standardized regression. Okay, we have just, the example will explain it clearly. So here we have a problem related to Efteling, waiting time at the Efteling. So we want to explain the perception of waiting time among customers of the Efteling. And we want to understand what's the most important factor that actually affects the perception of the waiting time. So it's not necessarily the time that passed when you were on the line, but it's more about your perception of the waiting time. And here you have this dependent variable perception of waiting time, which is on the Likert scale. And notice that this 1 is a long waiting time and 10 is a short waiting time. Okay. And independence variables, you have actual minutes of waiting. So this is really like an objective measurement of how much you waited. If the information is available about the waiting times at the lines, yes, no. So it's dummy. Distraction is whether distraction in the line, yes, no. And layout and design of waiting rows. This is if the participants of the survey disliked it or liked it. Annoyance, in general, if the response were annoyed or not. The 1 is not annoyed and 6 was very annoyed. We have responses from 100 people. So in this case, we want to understand this direct effect for multiple independent variables on the dependent variable, which is the perceived waiting time in Efteling. We have actual minutes of waiting, which we expect a negative relationship, because if you remember the perceived waiting time, the long label was 1, and then you had 10 for the short. So that's why you actually expect a negative effect here. Information available, it will it's natural to expect that when there is information available, the perception will be that the waiting time was shorter. Same with distraction and layout and like good layout and design of the waiting rows. And annoyance will, of course, increase the perception of long waiting time. So we expect a negative relationship. So these are our expectations, basically, intuitive expectations. Before we fit the model. And our model equation is that we have basically 5 independence variables. So we will get all of them and plus an intercept, as always, and we have an error. We need to estimate 6 parameters actually from this model. So we will have intercept, the estimate for the first independence variable, second independence variable, etc. And we have 2 dummy variables, which are information available, yes or no. Was there distraction in the line, yes or no? So this is a combination of metric variable and nominal variables in this case. As always, we just use this LM function to fit a regression model. So the perceived time, which is a dependence variable, tilde, actual time, annoyance, distraction, info, and layout. on the DF complete data set. Once we fit this model, we can get the summary output out of that. And now we can actually focus on the interpretation of these coefficients. So what we want to understand, if you remember the research question, which of these factors actually affect the perception of the waiting times more. But the issue is that, first of all, some of these are dummy variables. Second, the measurements of these are actually on different scales from time to time, right? Like you have 1 to 10, dislike and like, and 1 to 6. So 1 unit increase in annoyance versus layout, for instance, does not actually mean the same distance difference in the in people's ratings. Okay, and then you come to this situation where 1 unit increase in layout and info doesn't mean the same thing. So you don't actually know if this 0.2 and 0.3 is indeed, like, if actually layout affects it's more than information, or like maybe another example is annoyance versus layout. Okay, you don't know if these, like, 1 unit increase means the same thing. To be able to actually bring them onto the same level, so when you want to say 1 unit increase, it means the same for all of the independent variables. Then you use what's called standardized variables or standardized coefficients. In the case of unstandardized coefficients, so what we just saw, okay, we didn't do anything, we just use our data as is. Then the interpretation of the coefficient is, if you remember, is the 1 unit change in the dependent variable, the unit change in the dependent variable by 1 unit increase in the independent variable. So how many units change in dependent variable if you increase independent variable by 1 unit, keeping everything else constant. In the case of standardized coefficients, what we will do is the interpretation will be that what happens to the what happens to the dependent variable, how many standard deviations will it change if we change the independent variable 1 standard deviation? So then the standard deviation here will be uniform across at least the metric variables, that 1 unit change will always be in one standard deviation change. Okay? And how do we reach that actually? You basically use the standardized variables, standardized metric variables in your regression. You basically take out the mean from each observation. So we had, for instance, the real waiting time, right? So for each person, real waiting time minus the average of all of these people for the waiting time, divided by the standard deviation of the waiting times in your data. And you do all this only for metric variables, because if, as you remember, mean and standard deviation is only meaningful for metric variables. You do this for both independent variable and dependent variables. In the, and once you do that, you actually can compare if, like, which of these factors are affecting the perception of waiting time more or less. And as complicated as it looks, it's actually quite close to implement it in R. But it's important to know what's happening behind the standardization. So X minus mean over standard deviation. The way you do this in R is for each metric variable, and it's important because we also have dummy variables here. For each metric variable, then you put the scale function for each of them, and just write the model equation again. So scale perceived time tilde scale actual time, scale annoyance, and scale layout. And distraction and info stays the same because they are dummy variables. So no recoding needed. You can also recode it. It's not an issue. So then the sign of the estimate will flip. In this case, you don't have to recode. If you are going to do a reliability analysis, for instance, then you don't need to recode. But for the effects, once you understand the measurement of the things, then you don't need to recode. And we will also see soon that this minuses and pluses, we will not actually look at them. So we will only look at the absolute values to compare the estimates. Okay, so now now that we have the standardized coefficients, we can actually compare them. And the comparison should be among the ones who are significant, because if they are not significant, what was our conclusion? The conclusion is that they are not significantly different than 0. For the why does actual time has the biggest effect because of the p-value? No, we will. I'm just explaining that. So the p-value, you simply focus on the coefficient estimates with significant p-values, so less than 0.05. Then you look at the absolute value of the estimates. This means, for instance, for actual time, if you increase actual time by 1 standard deviation, you decrease, like the perception, not you, but the perception of the waiting time decreases by 0.45 standard deviation. If you increase annoyance by 1 standard deviation, you decrease the perception of the waiting time decreases by 0.17 standard deviation. So this decrease and increase is related to the sign, as we know. But in terms of which variable is the most important, we are interested in the size of the effect, not necessarily the direction of the effect. So if we compare among the significant ones, so actual time, annoyance, and layout, we can easily see that this actual time, because it has the biggest estimates and that biggest absolute into absolute terms, then we can conclude that actual time is actually the most important factor that affects the perceived waiting time. I hope it makes sense now, Nastya. And I also want to make an important point here for the intercept, because this is also the time where we see dummy variables together with metric variables in a regression. So here, the intercept will always have the same meaning, in the sense, same generic meaning. It is always the mean value of the dependent variable when all of the independent variables are 0. But when you have a standardized regression, what happens is that because you map this 0 to the original variable mean, because when it's 0, you actually take out the mean of these variable, if you remember the standardization, which we just saw, right? So x minus mean over standard deviation. When you actually set these variables, the scaled variables, to 0, you set them to their means. Okay, so the intercept here represents when all of these are 0, so that's always true. But here, when you set actual time, like the standardized actual time, to 0, you actually set actual time to its mean. Then what does it mean? So for the also dummy variables, intercepts represent the reference group, right? So when you set distraction and info to 0, this goes to their reference group. And because these are, I think, coded yes and no, yes here. So the reference group is no. Then the intercept, although it's insignificant, if it was significant, it represents the mean perceived waiting time, so the mean of the dependent variable at the mean of actual time, annoyance, and layout when there is no distraction and no information available. Okay? So is this clear? When you have a standardized regression and dummy variables, the intercept has a different meaning in terms of that particular regression. But you can always find that meaning in this particular case by using this generic notion of intercept, right? Intercept is the mean dependent variable, mean the value of the dependent variable when all of the independent variables are 0. So now we need to actually dissect and look at what it means that all independent variables are 0. Here, if we, like when we say the standardized actual time, standardized annoyance, and standardized layout is 0, it actually means that actual time is at the mean, annoyance is at the mean, and layout is set to its mean, okay? And for distraction and information, it means that we set it to the reference group, their reference group. And in this case, the reference group is no. So there is no distraction and no information. Once we combine this information of what it means that all of the IVs are 0, we get to the true meaning of the intercept in this context. And it means that the mean perceived waiting time at mean of actual time, annoyance, and layout when there is no distraction and no information available. Yes, this is the point where we are taking a break. We can meet at 10 past 10. Yes, indeed, the reference group is no because these two, distraction and information, are dummy variables. So the dummies are not set to their mean because they are not metric variables, right? So logically also the mean is not defined for a nominal variable. When you set dummy to 0, you basically set it to its reference group. So the intercept will always represent the reference group. But here, because we have two dummy variables and we set both of them to 0, it means the condition of no distraction and no information. But how do you set the reference group to no? So in this case, it is if you don't do anything in R, it will always set the alphabetically first one to reference group. So in the case of no, yes, no comes alphabetically first. So R automatically sets that as the reference group. But you can also use this relevel function that we have seen yesterday to set it specifically to no. Yes, exactly. So actual time, annoyance, and layout are standardized, and the rest are dummy. And you can also see that through the scale function here. So the way to standardize metric variables is to use scale both for the dependent variable and for the independent variables. But the independent variables has to be metric for you to be able to standardize. Because mean and standard deviation it's not meaningful for dummy variables. Okay, so for correlation, how can you tell if there is a spurious relationship? The spurious relationship can happen when you see a correlation between two variables. So the original correlation test is significant. But then in the partial correlation test, like when you add a third variable and control for that, if you don't see a relationship between the original two, so let's say we are interested in the correlation between variable 1 and variable 2, okay? You do a correlation test between variable 1 and 2, you see a significant correlation. Then there is another, like third variable, variable 3. Then you actually want to understand if this correlation between 1 and 2 holds when you control for variable 3. So then you do a partial correlation test. If that partial correlation test is significant, it shows that this correlation between 1 and 2 is real. Like it's there, even if you control for the third one. But if the correlation becomes insignificant in the partial correlation test, then you can conclude that the correlation between 1 and 2 was actually because 3 affected both of them. So then you can conclude that this relationship between 1 and 2 is spurious. Okay, so explain how standardization sets. So here, if you see that with this transformation, you subtract mean from each of the observation. And if this is 0, then you basically set this to its mean. So mean minus mean is equal to 0. So maybe did I make a mistake here? Setting a standardized variable to 0 sets the original variable to its mean. No, this is correct. So here, how does this standardized variable become 0? Because we set this to 0, right? It means that we set this original variable to its mean. Does that make sense? So if this original observation is at the mean of this variable, so if let's say it's annoyance, the mean level of annoyance, then the standardized annoyance will be 0. So that's kind of the relationship between the two. And because in the interpretation of intercept, we say that we set all of the independent variables to 0, it means that for the scaled variables or the standardized variables, we set the original variable to its mean. Okay. Good. Let's see you in 4 minutes. Okay, so let's continue with trend variables and forecasting, and this will serve double purpose. We will also talk about transformations here. So when we start regression, we said that the objective is to quantify relationship between a dependent variable and one or more independent variables. And we talked a lot about this understanding and explaining how a predictor variable influences DV. So when we talk about coefficient estimates, for instance, we always try to understand how a unit change in the independent variable affects the dependent variable. So, and this is also the focus of most of the academic work. But there is another use, and especially in the industry, that you can actually use it for prediction or forecasting. We have already did a little bit of prediction, right? So this point predictions, if you remember from yesterday, for the credit cards example, we actually did predictions based on the regression line that we get out of the LM function. And yeah, I mean, companies use this for many purposes to track consumer characteristics and behavior through time. They don't necessarily, they are not necessarily interested in explaining very rigorously what is the relationship between the two, but they really want to understand, for instance, what will be our sales in the next quarter. And with this, because we are going to talk about trend variables, let's also talk about what kind of data it requires. So cross-section versus time series. So far we have been looking at what's called the cross-section data. So data from units observed at the same time or in the same time period. So our level of observation is related to an element. So that's like, it could be a respondent, could be, I don't know, buildings, firms, etc. But if you also have a time dimension, if you have a time dimension as opposed to different units, then this is called a time series data. So you have one unit observed, so it can be, for instance, a country. Then you take measurements in successive periods. So that you have some examples here. This can be an income of an individual over his career, sales of a company over a year, and economy of a country over years, for instance. And if you compare both, then you come to panel data. So you have repeated measurements from the same units, same people, same elements, same firms, etc. So if we look at, for instance, the GDP of the Netherlands 3 years, and this represents our data, then this is a time series data. But if we look at, I don't know, 100 GDP of 100 countries through years, then this will represent a panel data because it has a cross-section and also a time element. So let's now think about an example. So let's say we observe sales from Amazon.com 3 years, and it is from 2004 to 2016. Now we want to understand, or the company wants to understand, what's going to be the sales in 2017. So you can already see that the sales has been increasing till 2016. To be able to understand this, we will introduce what's called a trend variable. So we will actually label 2004 as year one, and we will increase this variable 1 unit as we move along the years. So 2004 is 1, 2005 is 2, etc. So this is apparently the 14th year that we want to understand what will be the sales. And this is called then a trend regression, because we will include this trend variable in the model as our explanatory variable. So this y, the sales, is equal to beta 0 plus beta 1 times trend plus an error term. And this beta 1 then will represent the change in sales when there is a unit change in trend variable. And if you remember what was the change, 1 unit change in the trend variable is actually a year increase in time. So when we look at the relationship between sales and trend, we see that there's an increasing relationship indeed, but this is also not exactly linear. But just for the sake of it, let's fit a linear model to this data. When we do that, we again just use an LM function, sales tilde trend. We have just one explanatory variable or one independent variable, and we use this time series data. And we use the summary function to look at the summary output from this model. Here you can see that the trend variable is the coefficient estimate for the trend variable is actually significant. So p-value is less than 0.05. So we can conclude that this coefficient is significant, and a 1 unit increase in trend increases increases the sales by 10.25. So let's now, and as I mentioned, this 1 unit increase in trend actually means that, because how we defined it, this 1 unit increase in trend means that 1 year increase, basically. As a year passes, the sales will increase by 10.25. And for this, as always, we can actually look at predicted values and the prediction errors as well. So for each of these observations, we can actually get the predicted sales based on our linear regression model. And this is also what I meant, like what we have seen so far with the assumptions. So these are actually the fitted values, just to make that connection. And for each of them, we actually see this negative sales at the beginning and then very high sales towards the end. And it looks like this from this negative, so we get, and our final prediction for the year that we don't observe is 120.6. So this is our prediction, 121, and apparently we actually know, or next, like in 2017, we observed that the actual sales is 178, basically. So we have an error, but we are not super far off, maybe. I mean, it depends on what you, if 50 is a big number or not. Let's look at this diagnostics for the regression assumptions now. We have seen the sales and we can look at sales and predicted or residuals and predicted, and this is indeed more common. We have been looking at this so far in the assumptions more closely. And here, as you can see, that these lines, these points are not following a straight line, right? So this is the 0 points. So this is where we want residues to be aligned and straight if we have a linear relationship. And here you can see that the residues are actually, like at first, the residuals are very high, then they go close to 0, then they actually increase on the negative side, then they increase, then they go back to 0. So around here, our actually prediction error is quite low, but then it also increases again. We will address this issue of nonlinearity with two transformations. One is the log transformation of the dependent variable, and the other one is that we will add quadratic terms for the independent variable trend. For the log transformation, let's first look at that. Log transformation means that we actually take the log of what we actually observe. In this case, the dependent variable is sales. If you look at sales versus log sales, you see this kind of a decreasing return for the same increase in sales kind of relationship. So this is the log function, if you remember. When we looked at sales versus trend, we saw this exponential relationship. So that's actually how you can already see that the log transformation might work. Because when we take the log of the sales, the relationship between log sales and trend is actually more linear, right? So this is what we will leverage, what we will capitalize on. The relationship between log sales and trend is linear. So we can actually use a linear regression model to represent this relationship. Does that make sense? Because when the sales versus trends, this relationship was nonlinear, and we fit a model on this here. We saw that this model, while it's the linearity assumption. Now, if we take a log transformation of sales and look at its how it like the scatter plot of that with trend, we see that there's a linear relationship. How we can do this is we will now fit a model for the log transformed sales, and we will just use the same trend variable as the exponential variable. Here you can see that this is what we observed, sales in $1 billion, okay? And then take log of these. These are the log transformed sales. And we still have our trend variable here. The way to do this in R is that you actually use the log function, log sales tilde trend for the time series data. And you just use, again, the lm function, you get the summary output. So here, let's talk about this coefficient estimate. We see that the coefficient estimate is significantly different than 0. And then it is 0.2526. What does this mean? So this means that with 1 unit increase in trend, or in other words, as like within 1 year, log sales increases by 0.25. Not sales, but log sales. The log transformed sales increases by 0.25 because our dependent variable here is the log transformed sales. Good. So when we have this, of course, like once we make this interpretation, it's not super clear what happens to sales, right? Because we talk about the relationship between log sales and the trend. But what we really want to understand is what happens to the sales. There's an easy back transformation to actually look at what happens to the sales. So what's the relationship of sales and the trend, or any other independent variable that you might have in another example? Again, looking at this, looking at our data, we have sales, log transform sales, and then we make a prediction of this log transform sales with the model that we estimated. And here you see the results of that. Basically, this is plugging in the trend variable into the model equation, the fitted regression line. So one for the first period, basically, this will be 1.67 plus 0.25 times 1, or for the second trend variable, like if we are talking about the second year, then we will say, okay, 0.25 times 2 plus the intercept. Okay, this is how you calculate that predicted log sales. And what is really critical here to actually back transform it to sales. And the way to back transform, if you remember, if you take an exponential of the log variable, then you actually go back to the original variable. So e to the power log y is actually y itself. So then you can actually use this x function in R to on the predicted values of the log sales to transform it back to the original y. So when log sales is 2, the sales is apparently $7.3 billion. You do this for all of the observations in your data to get these predictions. And lastly, because we are interested in 2017, we plug in 14 as a trend variable. We get 5.2 as the log sales. And then if we take an exponent of that, we get we transform it back to regular sales. So here our prediction is 174. And if you remember, the actual sales was 178. So we now get to a very close prediction, actually, compared to the previous prediction, which was around 120. So this is very, very much like way more accurate. Then we can again look at the diagnostic plots, right? For the log sales and for the log transform model. And here, as you can see, we actually see this random cloud of residuals along the predicted values, or this is the fitted values, basically. If you use plots on this fit2, so plot fit2 1, comma 1, you will also get to this, the same plot. But here we see this random cloud of points, so the linearity assumption is actually satisfied here. Okay, so this is how the log transformation works. We introduced this here with a trend variable, but it might be that you just have a regular independent variable. But one important thing is about the zero values. So if you remember, the log of 0 is actually undefined. So in R, if you take a log of 0, this will give you a minus infinity. And if you have 0 in your data, so this is what's going to happen if you just take the log transformation. Or it's also important to consider if what you observe in your variable for that variable, if 0 is a meaningful value or not. It's very common to use this addition of 1 when you take the log transformation. So instead of taking log x, you get you take the transformation of log x plus 1. So because then you actually map 0 to 0 again. So log 0 plus 1, log 1 is equal to 0. It is also possible to take other additions, other constant additions for the log transformation, but it's important to specify this constant, like what you're using, and use that correctly also in the back transformation. Because if you take x log x plus 1, so here, then you will be left with x plus 1. So you need to actually subtract that 1 again once you back transform. Okay, but in the exam, I assume that we will not be able to see the table with all numerical data. So how would we know that predicted sales are? So it might be that we just what do you mean? Like once you have this, once you have this output, you can basically use this coefficient estimate to calculate what the prediction is for the 14th year. And then that's basically your predicted sales, right? So 0.25 times 14 plus 1.67 will be equal to your log transformed sales, so 5.2. And then if you take x 5.2, then it will give you the prediction. So you will indeed need to do the back transformation. But yeah, so it's of course, this will not be the case in a normal R output question. This will be the case if you if this is an R coding question, and then we might ask to make that back transformation. Yes, you need to know the log function for sure. What's the benefit of taking these additions? As I mentioned, the log 0 is undefined, and you cannot put this undefined values in the regression model because it's minus infinity. Then it will not give you a, like, you cannot fit a model based on a minus infinity data point. Do we have to do this on our own in the exam? Yeah, you might. If we ask a question about log transformation, then you will need to. Okay, let's now quickly look at quadratic terms, how we can add them in a model. So now, instead of taking a log transformation on dependence variable, we will look at how we can use trend variable plus trend variable squared in this regression. Then the meaning of, like, we will have intercept, and the meaning of this quadratic term plus the regular term is a bit more complicated because you cannot change the trend by not changing, like you cannot change the trend by and keep constant the square term of the trend. So this means the change in sales when a unit change in trend variable, so beta 1, plus the change in sales when a unit change in trend variable beta 2 times the trend itself. Okay, so a unit change in the trend will mean that you increase beta 1, like you increase this by 1, but it also means that you change this trend square by trend variable, like the beta 2 times trend 1. Yes, again, not super easy to interpret because you cannot change, you cannot talk about the 1 unit increase in IV, how it changes dV, without talking about the level of the trend variable. Okay, so what we will do here is that we will take squares to prepare our data for the regression. We will take square of the variables, the trend variable, so 1, 4, 9, 16, etc. And we will regress the sales on trend and trend squared. So the trend squared is basically this part, this column. Yes. Okay. The page not on zero values and log transformation. Yes, then I will add that. So I will post a new version of this with that slide added. Thank you. So we add trend and trend squared with, and we use again the same data. We get the summary output here. Then we have this coefficient estimate for trend and coefficient estimate for trend squared. And this actually means that a unit increase in trend, so it also means passing of a year, changes the sales by minus 32 3.32 plus 0.96 times the trend itself. This means that the effect of the change of a year is actually depends on which year you're in or which trend you're at. Okay, so going from 1 to 2 is not the same as going from 3 to 4 because you need to plug in the trends here. So to make it a bit more clear, you can also look at here. So this means that up until an inflection point, the trend will actually decrease the sales. So increasing years will decrease the sales, but then there will be an increase after an inflection point. Okay, so this means that up until this actually 3.32 over 0.69. So once this breaks even with minus 3.32, you will observe a decrease because this is a negative coefficient. And then after some points, this will start to increase. So this means that as years pass, sales will first decrease and then after turning point, it increases. So based on this, we can also get the predicted sales out of that. So this is basically plugging in the numbers based on this equation, and we estimated this coefficient here. You can get the values for all of the years. I think they are not added here. But eventually, sorry, they're here. Yes. So eventually our prediction for the years 2017 is 154.6, which is again close to the actual sales of 178, but it's not as close as when we took the log transformation. So the prediction is indeed more accurate than when we assumed that the sales trend relationship was linear, but it's not as good as when we took the log transformation. And when you look at the predicted values and residuals, you actually see that although this is, I mean, there is no particular pattern in terms of residuals. And then you can see that this can be, yeah, I mean, it's not super clear here, as clear as it was in the log transformed version. But seeing this random cloud of residuals is a good sign also for linearity. So this is distributed almost evenly around 0. Good. And yeah, so for instance, this is a calculation, open calculation for the, let me double check the intercept here. Yes, it's indeed 10.95. Here, for instance, for the, this is the predicted line that you have, right? 10.95 plus, I mean, minus 3.32 times trend plus 0.97 trend squared. So if you want to predict the sales in 2025, then you need to convert this into the trend variable, which represents year number 22. So trend is 22. And this is what you will plug in the regression line. So for this year 2025, our prediction is that 10.95 plus like minus 3.32 times 22, and you take the square of that. So this is apparently $407 billion. And it's actually 2.6 times the sales of 2017. So there is actually a big increase from 2017 to 2025. Good. So this is the end of this lecture. Next lecture, we will talk about moderation. Today, we will not have a quiz. If you have any questions, we are, and there's 5 more minutes for the end of the lecture. Let me know. Okay, so we can end the lecture here then. As I told before, the assignment 4 will be posted today, but the deadline for assignment 3 is tomorrow because we have extended it. Thank you as well. Will we get to practice this transformation during the assignment? Yes, Nasya. You will see a log transformation in the assignment. Perfect. Okay, have a good day, everyone. Bye.